All right. Can everyone hear me okay?
Yeah, can I get this collab actually here? Or?
1, 2, 3?
Yeah, I think everyone can. Your question is if you can actually get a copy of this notebook, right?
Yeah.
Yeah.
You go on the SK-time GitHub. And you search for.
Yeah, I got it, but how to go to collab?
I'm going to help you.
Oh, sure.
If you just turn myself off.
If you go to the SK-time GitHub account, there's only like 4 repos on there. And this is
Just raise your hand and I'll be silent.
Yeah, sure, no problem. All right, hey, good afternoon, everyone. Thank you for being here. So my name is Jonathan. I've worked with Franz to help develop SK-time, which is what skbase was born out of. So what I'm going to talk about, Franz kind of gave you a high-level overview of some of the general methods and interfaces that are built into scikit-learn and then also SK-time. And so you sort of saw the end result of what they are. Just curious, who here has actually used scikit-learn or SK-time before? Okay, at least a few of you. So if you've used it, I mean, if you work with machine learning in Python, most people recognize it as probably the most popular tool that you typically use, to basically interact with ML. If you haven't used it, something you should probably know, if you actually want to build an ML toolbox, probably the easiest way to get other people to use it is to make it as sklearn-like as possible, because that's basically what everyone's already used to using. And so if you want to dramatically reduce the amount of developer overhead required, like the brain cells required to get yourself introduced into like a new framework, it's almost imperative that people almost need to use it exactly like sklearn. And so Franz talked about, right, some of the higher level interfaces, they're just kind of built into the library. So what I'm going to talk about is if you actually want to spin up your own ML code base, what some of these usage patterns actually look like if you want to implement them with skbase. All right, so let's go ahead and walk through this. So what we're going to use as an example, I'll point out this is meant to be a bit on the simplistic side, okay, just to make sure it's didactically clear. We're going to go ahead and implement a base class for permutations, and then we're going to make separate instances of that do bubble sorts and then also do data shuffling, okay? Right, again, this is not meant to be to represent the cutting edge of machine learning. It's to provide a very, very simple and clear example, so that way the usage patterns we're talking about will be clear. Because we don't actually have to want you to think about what's going inside the fit method. Okay, so you could perhaps point out how some of the examples we're giving are a little bit toyish, but that is actually the point, just to make sure we can focus on the most important details. All right, so take a look at some code. Okay, so the idea is, if you install skbase, you can import something called the BaseObject. This, in a lot of ways, is probably the bottom of the skbase code pyramid, if you will. So what we're going to do, we're going to create an empty class here called basePermuter. All right. This is really just an abstract, high-level class. One detail you want to bring your attention towards. Franz previously talked about the tag system, which is sort of a way to organize broader sets of details, between different classes across your code base. You can see it implemented right over here. All right, and then fit here is left empty. And then what we're doing, all right, we're creating a bubble sort class up here. Okay, notice here, we're also defining the tags. This one, if you notice, is slightly different. So the value for always sorts completely is set from false to true. You might actually just want to pay attention to that, because we're going to use that to highlight some of the details of skbase. All right, we're initializing it here with the constructor method. All right, so if it's a sort function, you can make something ascending or descending. And then finally here, I don't know if any of you are planning on applying for a new job and you want to pass the data structures and algos portions in the beginning, maybe you want to pay attention to this. If not, you can probably just ignore it, because you're probably not going to have to implement bubble sort from scratch anytime soon. All right, so the idea then, all right, so here's the underlying logic of fit, and then you return the array. All right, so if seeing is believing, this will actually go ahead and then sort the array for you. All right, so the idea then This is fairly simplistic. We have one method fit, and then it inherits from the base object. So when you inherit from base object, all right, if you've used scikit-learn before, and Franz mentioned this, right, you basically modify the parameters of an algorithm using get params and set params. And so this is basically already installed already once you inherit from base object, as you can see over here. All right, if you want to modify the parameters for a class, it's basically already built into the base object itself. All right, Franz also mentioned the tag system, which I will get to a little bit later here. Okay. And the next detail we're going to talk about here, right, is the shuffler class. Okay. And again, this is a bit of a simple example. This is just something that will take in input data and then just randomize the order for it. Okay. Something you might want to draw your attention to, just in terms of how skbase works and some of its underlying details. Let's go ahead. Let's go back up forward. All right. So in bubble sort, we are explicitly defining the tags right over here. All right. I'm sorry. In the base class over here, we're also setting them right over here like this. All right. But in the shuffler class down here, okay, they're not being determined at all. All right, so the idea is the tag system inside skbase is based upon inheritance. So if we look through this, okay, the tag system basically automatically inherits from the base class, which is the base permutation class. Whereas the tag system for the bubble sort use the ones that are user specified over here, like this. All right. One detail I might want to point out is in base scikit-learn, there's not really a tag system. But when skTime was built, oh, I'm so sorry. OK. Not something I use regularly. I apologize.
So it's a bit similar. I think it has matured at the same time. But the inheritance idea, I think, is originally from scikit-learn, if I'm not mistaken.
OK. OK. Thank you.
Did they add that in 1.0? Did they add that when they moved up to 1.0?
Oh, I don't know.
Last year.
Yeah, yeah.
It used to be, there used to be multiple tag systems, and it always said, oh, this is still experimental. But I think with around 1.0, it must have been fair.
Yeah. Yeah, so thank you. If I was operating on incorrect information, I apologize. You probably used to use an older version of scikit-learn, which doesn't have this. So thank you for the correction. Appreciate it.
Yeah, I might be wrong.
Yeah. I understand. How about this? We'll restrict our conversation to something I know is true. When we've actually sort of built things into skTime, the use of the tag system has actually been very, very helpful for creating useful abstractions that will kind of apply across the code base. So that I feel confident about. The other parts, we'll just kind of let that drift, and then we can circle back to it later on to determine its exact level of truth. All right. So the second thing we'll talk about here, all right, is basically defining configuration variables for a particular class. All right, so the idea is tags basically exist for developer functionality because it can allow you to define basically how different types of classes can be used at a very high level. And then also it's helpful for user functionality because users can use this to quickly search your code base to figure out what parts of the code base fit a certain criteria. So in the case of skTime, if you want to search for a particular algorithm, which basically only works with a particular sort of data input that's maybe nested or three-dimensional, you can sort of find out that information relatively quickly. Okay. Configuration variables, they're defined in a similar way. However, their use case is primarily for the end user. Okay. And then the idea behind a configuration variable is it's actually used to determine a particular class's behavior. Yeah?
You might address this going forward.
Yeah.
Do you have to do anything to register your tags so that your class becomes searchable?
No.
That just happens.
Yeah. It's built into skbase.
I'll show them. So there's some things you have to configure, you have to point to the directory root, for instance, or not the root.
Yeah. Yeah, one thing I'll point out, so I'm just kind of giving a brief high-level overview, and then in the third part of this tutorial, Franz is kind of going into a more involved example that'll kind of work with these things at a deeper level. Okay, so all right, so in this case, if we look over here, we're taking a look at bubble sort. You have the configuration variable. Again, the way you actually would define this is extremely similar to the tags. It just has a different variable name. And so then the idea, all right, once you set the configuration variable, okay, so same thing. So things like getConfig and setConfig are there in the same way. All right. But once you do this, the underlying display over here, by basically changing the configuration variable, the way it sort of displays itself inside your notebook will change. All right. So again, this is mostly about display, behavior, user functionality, just to kind of give users a bit more empowerment for the particular details of how a particular class might sort of display itself. So it's a way to basically assign the behavior of certain types of classes according to your own taste.
It could also be about data, output data formats.
Yes,
So
yeah.
it could still be the same data, but it could also be in a different shape.
Yes, yes. And maybe if you want to basically change like output from like a NumPy array to a data frame or something that's more user-friendly or something along those lines, that's also the sort of thing you might be able to change with a configuration. All right. So I think a few people mentioned they've used scikit-learn before. Other people haven't. A little bit of background information. So a lot of times, if you are building out a machine learning library, usually one of the most important details you have to consider is basically how your different classes or estimators are actually composed together inside of a larger pipeline. Because most of the time, there are going to have to be a few different pre-processing steps you might have to use before you can actually implement some sort of ML algorithm or tool. And so a lot of times, this is generally true across different libraries, just not scikit-learn. But some idea of a data processing pipeline is usually pretty important. Okay, because it's actually pretty unusual where your raw input data is going to be perfectly suited for whatever sort of analytical use case you might have to use. And so in scikit-learn, in skTime, there are pretty heavy uses of composite algorithms which actually chain different processing steps together. So what we're going to do here is just take a look at a very simple example of a sample pipeline, which is basically going to take the shuffling class and then the bubble sorting class and then chain them together inside one function call. Okay? Again, I think if you've worked with skTime or scikit-learn before, something like this will sort of maybe look like second nature to you. If you haven't really worked with these before, the syntax might be a little bit different, but it's definitely a design pattern which you see quite a bit. So the idea then, what we're doing is we're creating a meta class that actually takes in both of our base algorithms here, right, the shuffler and the sorter, and then we're actually chaining them together over here like this. Okay? This example is a bit simplistic, but most of the time, if you're actually working with, I would say almost anything, okay, in real life, it's very, very common. There's some sort of data processing step you're going to have to chain together with whatever it is that you want to do. All right, and so in a way that's pretty similar to how we actually defined the actual base classes which inherited right from the base permuter, here we're doing something which essentially acts like a pipeline and is actually able to chain together the operations of both permuters together. So that way the operations are performed successively.
It looks like a box disappeared. Maybe you want to show that getParent still works for this composite.
Sure.
Pipe.getParent, just add it.
Okay. Yep, I'm going to hope this thing is going to work correctly. Let's take a quick look.
It's on my computer.
Okay.
Probably on the
Real quickly, Franz.
Oh, it's German?
Yes, this is in German, so I can't quite demonstrate it.
Hello.
Okay, yeah, so the idea then, okay, thank you, Franz. Yeah, so if you're composing some sort of pipeline that wants to chain together multiple steps together, so the functionality of things like getting and setting parameters or configurations or tags also exists at the meta level for the pipeline itself versus the individual classes that we defined before. All right. So if you want to build a machine learning toolkit, probably the most universally used method across most major tools is something called fit, all right, which is basically what you call when you actually want to extract patterns from your data. In scikit-learn, you basically refer something that uses as the fit method you refer to as an estimator. And so if you're building with skbase and you want to build an estimator, again, which is something that would use the fit method, there's going to be a BaseEstimator class that you can go ahead and call on. Okay? BaseEstimator inherits from BaseObject. So we're going to take a look at our base permuter and then bubble sort class, this time inherited from BaseEstimator. Okay? Quite a few of these details are going to be about the same. Only thing that we're adding here, okay, a sort method, which is maybe a bit more semantic for what we're doing. And if we take a look over here at the bubble sort class, right, which is also inheriting from base permuter. Okay, inside the fit method, all right, we're doing two separate items. Okay. We're creating an attribute here, which is available after fitting. Okay, so if anyone's used scikit-learn before or skTime, basically the standard use pattern is that if you have some kind of model artifact that's available after you're done fitting, it's usually made available with a trailing underscore afterwards. And so we can see that over here. And then there's also an attribute, trailing underscore isFit is now set to true. So if you have code that's similar to this built into the fit method, should I run this? All right, there's going to be an isFitted attribute, which can return true or false. Okay, depending on whether or not you've actually fit your algorithm. And then likewise, after you're done fitting a model, a lot of times you will care a lot about what sorts of attributes are made available afterwards. So again, if you're using linear regression, this could be something like model coefficients or intercept terms. If you're using a decision tree, this could be something like feature importances that were determined afterwards. All right, but if you actually build with skbase, there's going to be the method getFitParams, which is automatically inherited from a BaseEstimator. All right, so last but not least, some of the built-in tooling for testing. All right, so this is an area that's maybe not the most exciting thing to cover, but is also quite important because good test coverage is obviously really critical to maintaining the health of your code base. So what we're going to do now is take a look at bubble sort, except this time we're going to go ahead and then add in a final class method here, all right, called getTestParams. And so the idea here is when you actually build a class with skbase using a BaseEstimator, you can define what sorts of parameters you actually want to use for testing later on. And so same thing. Once you initialize a class, actually you don't have to initialize, excuse me, because it's the class method. Maybe I did forget to run this. All right, but the test parameters will be made available to you. And then also what you'll be able to do as well is create a test instance that you can use for testing later on. And these will come pre-equipped with the parameter values that you set here, like that. Okay? So we can make sure everyone gets this notebook later on, but the idea is this is an introduction to the collection of utilities that you have available to you when you actually want to go and start building with skbase. So thank you very much. And then I'm going to turn it back over to Franz, and he is going to actually walk you through how you might build an actual tool using the skbase tool.
Yeah, now we're going to build a package.
All right.
Thank you very much. I need to switch on this thing here. Can you hear me? Excellent. All right. So in this final part of the presentation, I will give a bit of a recipe on how you would build a package with skbase, which is the main use case, right, for developer use of the package. And so what I'm trying to showcase is how to build an scikit-learn-like package, which makes use of base classes, the strategy pattern and template pattern for the extender, tags and configs, retrieval, I think where we've already got a question. So how do we set up the retrieval functionality? Heterogeneous meta-estimators. Examples would be pipelines and composites that can take a varying number of object or estimator components, and how to set up the test framework, last but not least. And what we're going to do is follow a little bit of a recommended recipe. Now, it's my personal recommended recipe. You don't have to follow it, but I have been using it a couple of times. I think it's what's consolidated a little bit. Now, the first step comes from general software design recommendations. So before you start designing, before you start abstracting, it's good to have actually implemented, so at least thought about, but better actually implemented some examples of the algorithms you want to implement. And based on that, the general rule is, well, if you want to abstract, think at least about 3 substantially different examples that cover your space over which the design should vary, because that shows you, okay, do I need a parameter here? And there's always a trade-off between under-design, being too specific, being too close to the algorithm, and over-design, covering too many hypothetical cases that make your design too complex, and you don't really need that complexity. So next 2 steps, user contract and extension contract. What do I mean by this? The user contract would be the unified interface that a user would see. So in scikit-learn, that would be something like fit-predict for supervised tabular estimators, or fit-transform for your transformers, for instance. And including doc strings, so what are the types, what are the expected input, what is the expected output. Then the extension contract, right? Because we're building a package that is scikit-learn-like, so it should be easily possible to add more estimators of the same kind. So we need to write down, if you're an extender, where do you need to implement, what do you need to implement precisely? And these are the two sides, right? The extender side and the user side that needs to be written down, and can already be a base class design. Then you would start implementing using the base class architecture with meta classes, if applicable, the public interface, boilerplate, if any, template methods, tags, configs, and concrete classes based on that. Now, this might already be based on the examples you have. So you could start with the examples you have, define the interface, and then try refactor your examples, subject possibly even through functional equivalence tests to the abstract class interface of the scikit-learn-like framework. Then, okay, you might do this at the end to draw up the very systematic testing framework. Or you can do this earlier to the degree you are an adherent of test-driven design. But we probably don't want to do that earlier than number 5, because before that you don't even know what your interfaces would be. Now, retrieval will go about, we'll look into that, and also systematic testing. So, now, the package we're going to implement is not just scikit-learn-like. What I will try to show is how you would, based on scikit-base, implement something that actually covers the same use case as scikit-learn. And we're going to focus on regressors and transformers only, just to show the entire pathway. And why did I choose this example? Well, I hope most of you are already familiar with scikit-learn itself and the design. So the abstraction step from the examples, it will not be too unfamiliar. Now, you can, of course, try to do the same thing with the example from part 2, as an exercise if you want. Try to come up with a nice design for sorting algorithms, for instance. So, iteration 0, 3 example rule. So you would need 3 regressors, 3 transformers, 3 ways of composing estimators, right? So in this repository there is only 1 example, but if you would actually do this, you would try to write down 3 examples. Now, the different versions of the package, so as like in the cooking show, right, you start cooking and then, oh, we've already prepared it for you. Here is the cake which is almost done, and well, the other thing is burning. I'm not actually going to try to implement this on the fly. So here you can see them here in the subfolders of PyData_skbase, and this is something that you should also be able to run. The repository has its own requirements file and also lives on Binder. So linear regression, and this is not how you have it in scikit-learn, right? This is just linear regression, how you would fit the model. So you would return the coefficients. Right? If you can use the pseudo-inverse, then this is ordinary least squares regression with it's just a few lines, and then we return the coefficients. This is no intercept, right? Just to make things very simple. In a pandas data frame, used in the coefficients to predict. That's a simple matrix multiplication. Okay, that's linear regression. Now, the funny thing is I have the beta here, so that's, I will see if I start implementing other regressors, I'm not going to have the betas. The beta is actually a parameter, so I want this out of the predict. There's no parameter in the fit, but I can also already think, okay, do I want an intercept, yes or no? That might become a parameter of the fit, but I want to pull this out into the object. Yeah, and if I want to scale my data, here's another example, is a transformer. And now maybe I have modeled it, so I have a parameter where I can select how I want to scale it. It's a choice you can make. In scikit-learn proper, it's implemented as 2 different transformers, the min-max and the standard normal scaler, but you could also think about it as a single thing. Now this even is only a single function. It's not clearly separating a fitting and a transformation step. So this is just to show how you would start. So then you would draw up more examples, and you would say, oh, there's actually things that we're fitting here, right? These parameters here, they're the parameters we're fitting potentially. So I don't want to compute the minimum. I don't want to compute the mean or standard deviation on the test set. I want to compute it on the training set and then apply it to the test set and so on. So these are the design considerations by which you end up with something similar to scikit-learn. And I'm showing these thoughts to you in the example of scikit-learn, because you usually know scikit-learn, you already know the perfect answer in a sense to these design questions, and it's not always perfect, but it's pretty good in most of the places where design decisions have been made. But I want to show you that if you build your own package, then these are design considerations that you actually have to make from the very start, right? Why, for instance, this one scaling function, why you would or should separate this into a fit and a transform, it's not obvious, Right? Why in linear regression, the beta, it should be a parameter and not the input to the predict. That's not obvious. You see that if you have multiple pre-processing steps that you look at together. So that's why this 3 example rule is quite important. All right, so let's move on from, and this phase, by the way, it can take a lot of time. Good design can take a lot of iterations, a lot of iterations upon in the idea space and on the code base. First step, then think about the common base class interface. So based on the design, you would now come up with, and I'm of course dropping this from the heavens, like scikit-learn has dropped from the heavens, obviously, that you go with fit predict and fit transform as we know it. But now let's suppose we have decided on, based on the design, that this is what we want. So now we need to implement it as a base class. So what we would do, similar to how we've seen it in the second part, so we need to decide, okay, is it an object? Does it fit? Do we need the is fitted thing here or not? If it's just an object like a splitter, for instance, or you could also think about a loss function. That's an object. It doesn't get fitted. If it's an estimator, if it gets fitted, there's an ingestion step there. It's a BaseEstimator. In this case, the regressor is a BaseEstimator. So we have seen the sorting algorithm. You can consider both as an object and an estimator, depending on what your conceptual model is. The regressor is an estimator. Right, so you now define your interface, and what does interface definition mean? Right, you actually write the abstract doc string. And as we see, this is slightly different from how scikit-learn actually does it. Right? They're both data frames. Right? And so I do not want to go into any of the details on what is better here, because I'm fully aware that there have been heated discussions on the merits of NumPy and pandas and probably other things as well in scikit-learn. I'm just going to deviate slightly from certain established norms here, just to show how things are different. So in predict, of course, if the input here y is a data frame, then we need also to return a data frame here. Transformer, same thing. Right, the design sits here in the specification. I say, okay, here, what is written here to self is the underscore parameters. The state is not mutated by the transform and the predict method, and it should also have no side effects. I should have maybe written that in the doc string. So this is the first iteration, right? We're going to have multiple iterations on this design. Now we take our original code from iteration 0, and we can now implement a linear regressor here. Yeah? And okay, I've added a shrinkage parameter. I'm not sure whether I've actually implemented that, but you would just have to add here to the pseudo-inverse. And but what I've also done, I've added here some input checks for good measure, because in the specification, if you read the specification, it says, the x in predict or transform, it must have the same columns as in fit. So we want to check that, and in fit, the length of the x and the y, they must be the same. So we also want to check that. And the beta, it's a parameter. And we have conceptualized the coefficients as a fitted parameter, so now we need to write it to an attribute that ends in an underscore. And this comes from the scikit-base convention of the BaseEstimator. If you use a BaseEstimator, then the underscore is fitted parameter needs to be set to true by the fit method. That's convention, how scikit-base currently works. In predict, right, we do some of the checks, and these checks are based on the columns we've remembered from the x and fit. All right, so far so good. And here transform, right, this is fitting a number of things, and it's always computing these attributes, which one could also consider a questionable choice. Should we really always fit it or not? Again, just as an example, we now have one parameter, which is a strategy that we can choose here. That's again in deviation of scikit-learn proper. It might actually be a worse choice than scikit-learn proper, because as soon as you have a parameter that says which algorithm do I use, it hints at this is not dry, right? You might want to split this into two classes. But again, just for the sake of example, again we do some checking here. We can even do some checking in the init. And for people familiar on the developer side with scikit-learn, this might be either a no-go or a discouraged thing. Whereas and we do again some checks in fitting and predicting. All right, so this is a thing we can do. It's not exactly congruent with scikit-learn. I want to emphasize again, I'm not making any statements about what is better or not design-wise, just showcasing BaseObject that you can make these choices. For instance, this checking here in init, you can do that because in setparams, the init is actually being called. So it happens in setparams, init happens inside setparams. Now, on the user side, this is how it will look like. It looks like so we didn't implement any get params, right? We have pretty printing. Now the default here is HTML, whereas if you use scikit-learn proper, it will be text, and you can switch it around. You can use the get fitted params. That will give you the beta. It happens now to be, I think it says Panda series. Predict produces a data frame. Get params also works out of the box. Yeah, same with get fitted params. And so far so good. Now, are we done? Well, you've already seen here iteration 2. There's some more things we might want to do. So we have only thought about the user interface now. We have not thought about the person who wants to add a new algorithm. And let's think for a moment about the person who wants to add a new algorithm. What does this person have to do? Well, there's all this checking stuff we now suddenly need to copy-paste. That person, so now you would have to write, if you would write an extension template, which I have also done. So this is the extender contract. The extender contract is an extension template which describes how does the person who implements a new algorithm, what do they have to do? And I think it's good practice just to put here either in a separate piece of documentation, or if you don't want to go that fancy, you can just put a fill-in template, which we also have in skTime, and it exists for scikit-learn. I think it's the ancestor of these templates. It says what do you have to add, right? You have to write parameters to self, you have to call super init, and then there is the stuff which is always the same. Right? Stuff is always the same. And then you insert the logic, you write the logic here. And again, here's stuff which is always the same, and you insert all the logic here. Now, from a design perspective, this is not very dry, because you're telling your extender, your developer who writes a new algorithm, oh, now just come on, copy-paste all this stuff here. And let's say you want to change all this stuff here, then you do not just have to go to all the places where all the stuff here currently is, because it has been copy-pasted all over the place. You also have to tell all your extenders, so potentially people who have written their own estimators in private code bases, well, from tomorrow, there's going to be an additional check here, and we're no longer going to raise a value error, but a type error, and you have to change all this in your custom estimator. So this is not very nice towards the extender. Right? The user doesn't see this, but the extender will curse you. So, and that motivates the second iteration on the extender interface. So the input check boilerplate is quite repetitive, and so it's not the only thing you can do here or need to do even. But one way to simplify the extension template is using the so-called template pattern. And a template pattern It's an object-oriented design pattern. The principle is you isolate the pieces of code that are always the same, and from there you call the variable part, and the extender implements only the variable part. And how this looks like is here in this iteration 2. So we put all the, in the base class, the base class is where we put the things that are all the same. All right, so we had these checks here, stuff and stuff, storing the columns, and in predict checking the columns that we've seen against the columns that we now see anew. And then we call the underscore method, so the templated method, and that's what now the implementer needs to add. So the extension template is now much friendlier. Right? It has the underscore here, so the implementer might wonder, where is this being called from? But they don't have to copy paste all this other stuff. And in scikit-base, this is also supported by the interface design of the BaseObject and the BaseEstimator, simply by how we deal with things like the fitted params, or the isFitted, or the state handling, say clone and reset. So reset, for instance, being called from the set params. Other things we can add also, why not in the same iteration? Let's add some tags. So regressor type, so we can search our estimator base, and we add also a config. So, and the config is enabled by now the template pattern, because now it's much easier to add configs in this boilerplate layer. Because let's say we want to convert the output to pandas. In the previous design, we would have had to copy paste this convert output a million times if we had a million estimators. Now we just write it once in the boilerplate layer that the implementer never gets to see. So here we could have had, say, version 42 where we didn't have this output conversion. In version 43, we add the config. Nothing changes for the concrete estimators that we have implemented, because we add this to the base class. And of course, we can factor this out in more complex methods that we call now from the boilerplate layer in the base class. Yeah, so the design for this boilerplate layer, this is now for scikit time. And you have the public interface, the fit, and you have the extender interface, that's the underscore fit. Both are friendly, right? The fit and predict is friendly to the user. The underscore fit and underscore predict is friendly to the implementer. So the learning curve for getting new contributors to your package is not as steep, because you don't have to know about these special input checks and conversions, and you have to write to this, you have to check that. That all sits in the boilerplate layer that only the most core of the developers need to know about. Now, of course, there's pros and cons doing it this way or doing it that way. They're saying this is a design decision you can make, and it's for SK time. I think it has been beneficial because of the complexity of the time series tasks. You have to do a lot of things there. You have funny data containers. It's not just plain NumPy in many cases, or even pandas. And even then, you might want to go with the so having even some functionality in this boilerplate layer, like iteration over instances or dimensions. Broadcasting. Anyway, from the user perspective, not much has changed. Still looks and feels the same. You can inspect tags, of course, if you want. All right, iteration 3. So this is now concrete estimators. It's the base class design itself. Let's now talk about composites, pipelines, meta-estimators. How do you implement those? And so there are some classes in scikit-base which we haven't seen yet, namely the BaseEstimator. All right. And the BaseMetaObject. They are very similar to the meta-estimator in scikit-learn if you know the internals, but exposed in a way where you can use them as templated components for your own machine learning package. Now, the estimator class works as follows. They have tags. There's two tags, the named object parameters and fitted named object parameters. These are strings that tell the estimator where to look for a list of name estimator pairs, like in the scikit-learn pipeline. So I first show now how this is going to be used before showing how it's implemented, because it might not be entirely clear what we want to implement here. So we want to implement a regressor pipeline that if given a list of either estimators or a list of name estimator tuples, will produce the known behavior of a pipeline with the get params and fit. Right? So if we fit the pipeline, it has, in this case, well, we don't have a lot of pre-processing steps. So I'm simply chaining two scalars here and the linear regression. It has the get fitted params behavior and does the obvious thing. So it first applies the transformers and then fit predicts them. So how do we implement that using scikit-base? Let's have a look at the new pipeline module. So nothing else changes except the pipeline module in this third iteration. Yeah. So, I forgot to complete the docstring. But this steps here, it can be a list of estimators or a list of name estimated pairs or a combination thereof. And what this will do is we'll apply first the transformers, so fit, transform, and then the supervised regressor with the fit, and then transform. It applies just the transform with the transformers, and then does the predict of the regressor. All right, so this is just checking logic. Don't worry about the checking logic. But what's important is that this base meta-estimator, it's used as a it's used as a replacement base class now. Yeah, so it inherits from BaseEstimator, and it also inherits internally in scikit-base from a meta-estimator mixin. And this mixin provides a number of utilities like the checker. So this checker, check objects, it clones the objects and it coerces them to name estimator tuple list. Before that, it could just have been an estimator list. And the get names and objects, it's basically just a fancy zip on top of the tuple estimator list, but it also coerces if it needs to. So then you can implement your custom logic on top of that to get you the index where the regressor sits, and otherwise raise an error. In underscore fit, again, so we have dealt with all the checking and conversion. All we do is implement the logic. This is the logic of a pipeline, basically, and we call not the underscore fit, we call the fit. And in predict, it's just sequential application, really. Now, this is the pipeline, and the other thing we need to do, we look in the base class. So now we have the base meta-estimator. We're inheriting this from scikit-base meta-estimator, and also now we would notice we would need to put these tags both in the BaseEstimator and the base meta-estimator, but we can just get them from a common mixin because tag and config inheritance is by element. So return type, and we can just put them in and don't worry about these attributes being overwritten by, for instance, this one here, right? So this is not the estimator, this attribute. It does not, if you use get tags to access the tags, it does not override these tags, as we have previously seen. And that's why we can factor it out into, whoops, this one here. OK, so now we have implemented our meta-estimator. And again, it didn't take long. If you know how to use a scikit-base, you can take this as a template if you want. All right, so now the lookup and search functionality that we also want to add to our package. That's iteration number 4. And the way to do this is using all objects in skbase. That is a utility which basically does all the crawling and filtering for you. And you can look at the docstring of it, of course. All you need to do is interface it and set some of the parameters. So the important bits are pointing to the right directory, excluding directories, for instance, where your extension templates sit, maybe where your test fixtures sit. And if you want also to be able to search by a string for regressor, you need to map these onto a registry, but this is not necessary. You can also use classes, or you can use tags for subsetting. So if your type, your regressor, your estimated type already sits in a tag, you don't actually need to write a registry. So it works out of the box. The way it will work is, right, you have this magic function on estimators, and this gets you all the estimators from, so anything that inherits from BaseObject. In your package, you can use it to filter by tags. So you can say, oh, I only want the regressors in my package. Yeah. Or you can also do this by providing the class directly here. Now, internally, I have said this is, so the function is called all objects, because not all the objects are estimators. But of course, you might want to use it only for estimators. There's just a small distinction. Just need to be careful about the difference between objects and estimators. Now, this docstring is just mirroring the docstring. It's mostly a copy-paste of the docstring of scikit-base all objects. So what estimator types do you want? An argument to filter by tags, an argument to exclude from estimators. Do you want to return as tuples or data frame? Do you also want to have some tags listed in the return table, which might be useful if you're trying to tabulate here? And all it does really is interfacing the all objects. If you want to have some syntactic sugar, so if you type regressor as a string, it knows, okay, I have to inherit from base regressor. But you don't need to do that if your estimator type sits in a tag. The important bit here is pointed to the package root directory. So I have just sneakily pointed it to a relative path. It might, depending on your setup, you might have to fiddle around with this argument here. And of course, we want to ignore the tests and the extension templates, because the extension templates, they're not complete. Right, so if you even try to import that, so if you ignore the modules, it doesn't even try to import it. So if you have broken code in there, like you might have in extension templates, it's not trying to import it, and the utility is not going to throw an exception. All right. Last but not least, testing. Just quickly brush over it. So you might do this earlier or not. The only thing this iteration adds is a test class, which is seen by PyTest. So your PyTest CI runs or local PyTest runs will find the class. And what this class does, it tests the BaseObject interface contract. So for instance, are all the parameters being written to self in init? Things like that. Do you call super init? Or do you move into the BaseObject init? This is all tested by test.all objects. You can also write your own tests and your check estimator utility. Right, so you can call the test class directly. And you get some basic testing functionality for the BaseObject interface. And here we also have defined our own test for the linear regression class. And the example here in the tests, it shows how to set this up. So you need to configure the package, where the package sits, objects you want to exclude, so again, extension templates. If you want your tags to be checked for validity, right, this is something you need to add here. The test all objects, you can just inherit this from test all objects, and if you want to add your own tests, there are certain arguments that the test class already provides for your tests. So object instance, so you might have been wondering, okay, what is this create test instances and names in part 2? What is this good for? Well, this class, the base fixture generator, it loops through all the test instances and exposes them as object instance. So this test is executed for all test instances, and there is more refined functionality where, for instance, you can generate data based on properties of the object instance. It's not shown in this tutorial, but if you want to see some examples, you can look into the skTime test framework. It's explained there. And of course, if you want this to be tested only for regressors, then there is the object type filter variable. So all the config variables for the testing framework, you can also look at them by looking at the test all objects in the skbase repository. It's not as well documented as one might like, but coming back to what I said at the very start, contributions are very much appreciated. Right, this skTime, skbase, they're both openly governed, openly led projects which invite contributions by everyone. Scikit-base hopefully will be useful to you as a reusable workbench for creating scikit-learn-like, scikit-learn, scikit-time compatible libraries. We've gone through how to create your own package with public interface, extension templates, how to use a tag config and testing system. Most of it works out of the box. It needs a little bit of adaptation, hopefully taking a lot of the time from the case, the alternative where you would build this all manually. All right, I've already said this. skTime is openly governed. If you would like to contribute, please let me know if you want to get started with contributions to open source in general, or skTime, or skbase. Feel free to find me here at the conference. I'm still here until Friday at the very end. The regular community collaborations for skTime and skbase on Fridays, you just go on the GitHub, go on the Discord, join, send me or any of the other developers post in the channel, or send a private message at Fridays 4 p.m. UTC, which would work for most time zones. There's an open developer and contributor meetup on the Discord. We're going to have mentoring and internships again this summer. There is opportunities for some paid summer internship slots as well. There's unpaid mentoring. So the proposition there is you invest some time for contributing, and in turn you're mentored by an experienced developer. If you want to learn more about those, look on the skTime/mentoring repository. There's always also a list of the current opportunities for more structured mentored contributions or internships there. An onboarding session for skTime contributions will be held in June. That's coincident with the start of the summer internship cohort. And there's going to be a developer sprint, location TBD, possibly virtual, in July 2023. So, more than happy if you'd like to join. If you also would like to get our help in building your own package, we're here. You can contact us or just go on Discord and let us know. All right, any questions in the remaining half minute?
Two. So this is really informative. It's good about.
So I'm not sure if you recorded, but do you want to? Maybe this is. So just so it's recorded also.
Fair. So this is really informative and about how to build this sort of tree structure with the inheritance and yada yada. The thing that I'm sort of missing here is what are we getting by using skbase that we're not getting by using like just the mixins that are provided in the sklearn base? Like, because we have, like the regressor mixins and stuff like that that add that sort of functionality.
Oh, sure. So the meta level. So if you use I think, so of course, BaseEstimator from scikit-learn is also something you can use, obviously, but that gets you all the fit stuff, and it gets you idiosyncrasies around the tag and the config system. So I think the config is quite tied to the specific estimator types, which are in scikit-learn. Now, I have been in the past, actually that's how it started. For scikit time, we just used BaseEstimator. We just inherited everything from BaseEstimator. And then we started bumping into all these idiosyncrasies, specifics of scikit-learn where it didn't quite work as we wanted. The tags were working in a funny way, and we wanted to define our own tags, and we wanted to control behavior. So we started increasingly replacing functionality in the scikit-learn BaseEstimator by more abstract functionality. Right? And then in the process, we abstracted away most, or like, let's say 60% of the scikit-learn BaseEstimator, and then we thought, well, if we now copy the rest, then we actually have a quite nice templating framework. And so also people from the SK-Time community started using it then for their work projects, where, for instance, you have to define a specific kind of algorithm for which there isn't a toolbox out there, and it's really sector specific. So, okay, you can take BaseEstimator, but then you will run into the same side issues again. So I'm not saying BaseEstimator is unusable. No, it's actually excellent. You can just import BaseEstimator, and you have pretty printing, you have the composition already. But some of the things you've mentioned, right, iron tag system, fitted parameters. Right? So for instance, in time series, you want to inspect the fitted parameters. You have parameter estimation, and you want to plug them in. Say in other estimators, if you want to do, say, auto ARIMA or auto ETS or automatic seasonality detection, and the seasonality you want to plug into another estimator, well, either you need to have used the same attribute or done some attribute magic, or you have something like get fitted params, which makes it easier.
If I could follow that up.
Any other questions, maybe? All right, of course.
Okay, so am I correct in inferring from your answer that there are conflicts, name conflicts between skbase and the mixins from scikit-learn.base, and you could potentially use them both, but then you have to check the order of your inheritance because it affects the MRO.
Yeah.
I bet that was a simple one.
So skbase is not inheriting from scikit-learn.
Right.
Yeah, but it is fully compatible.
Fair. I could create a class that inherits from both skbase and scikit-learn.base, right? But then which one wins when if I'm calling super depends on how I have them.
Yeah, but wait. If you inherit first from scikit-base, BaseEstimator, it overrides everything in scikit-learn. So it's a superset of functionality. The public interface is a superset of functionality as far as I know. So if you override scikit-learn BaseEstimator with scikit-base BaseEstimator, you basically get scikit-base BaseEstimator. If you do it the other way around, you break the functionality that is additional in scikit-base BaseEstimator.
All of it?
Not all of it.
What if I just really like your tag system?
You use BaseObject.
Yeah.
You override BaseEstimator from scikit-learn with BaseObject. Other questions? I'm out of time, right? I'm going to get thrown out and.
Seems like people are storming in, but.
Okay.
No, I guess that's it. Thank you so much, Franz. Thank you so much, Jonathan.
Well, thanks all for coming.